Right, so let's look at how we can write precipitation reactions. And of course, precipitation reactions or any kind of exchange reactions, it's important to remind ourselves of how the ions exchange and then what are the effects of those. So this example will specifically look at precipitation reactions and why we need to look or what we need to look. So we're of course using our solubility tables to tell us which species are soluble, not soluble, and how they interact. So this question basically just says, write a balanced net ionic equation to indicate what happens when, and then there's certain mixtures that are made. So starting with the first one, we have that calcium perchlorate and potassium sulfate are mixed. Now, calcium perchlorate is calcium ClO for 2, which is aqueous, because it says aqueous solution. So, I mean, it implies that they're solvated. And then potassium sulfate. So, sulfate is SO4. It's 2 minus, potassium is plus 1. So, have these. Right, and then in exchange reactions, we know we just swap the ions. So the perchlorate goes there, and the sulfate goes there. And then we see what we end up with. So we'll have calcium sulfate. We don't know its phase yet because we'll analyze that, and we'll have 2 potassium ClO4. Right. The reason for the 2 is because we have 2 potassium on the left and 2 perchlorate ions on the left as well. Okay, so now we need to check whether or not there are any solids, and then we can start looking at the net ionic equation. And you'll see most sulfates are not soluble, so that one is a solid, but the potassium, most salts of potassium, sodium of the first group metals are soluble, so this one is aqueous. Right, so that means then let's say, so the full total ionic equation then is as follows. So on the left-hand side, we split it. This becomes calcium 2 plus. I'm going to leave out the phases for now because it just makes it a bit easier. Plus then 2 multiplied, well, 2 ClO4 minus. Plus there's 2 potassium plus 1 sulfate. Gives us calcium sulfate. Solid, so it does not split. It's not dissolved. And again, 2 potassium plus 2 ClO4 minus. Okay, so that's our full or total ionic equation, the full total ionic equation. So it would generally just the full ionic equation or the total ionic equation, but then you have both. So that means then our net ionic equation, we need to eliminate certain species. So what is on the left-hand side and on the right-hand side? Well, the first thing, so let's go from left to right. So calcium, but there's no calcium 2 plus on the right-hand side. Perchlorate, there is perchlorate. So that means we can cancel them, and there's 2 on both sides. So that means that completely cancels. Potassium, yes, there's potassium left and right, and there's 2 on the left and the right-hand side. So we cancel that. And the sulfate, there's no sulfate. So that means our net ionic equation is calcium 2 plus aqueous plus SO4 2 minus aqueous, giving calcium sulfate in the solid state. Okay, and that's your net ionic equation. Remember, you eliminate the spectator ions. So the spectator ions are the potassium and the perchlorate. All right, so that's the first one. The second one says ammonium sulfate and zinc chloride. So B. So this is ammonia NH4 sulfate, and sulfate is 2 minus, so it means we need 2 ammonia because it's NH4 plus, and it's an aqueous solution, so it's definitely aqueous, plus zinc chloride. It indicates, yeah, zinc chloride, zinc is 2 plus, chloride is minus, and then, so I mean this will be aqueous as well, gives us 2 ammonia chloride, I mean there's a 2 in both of them. Phase is to be determined, plus zinc sulfate, also phase to be determined. So if we look up the ammonia chloride, we will see that yes, indeed, this is something that can dissolve, and the zinc sulfate is also something that can dissolve. So it means something interesting. So because if we're going to split all of this now to get our full ionic equation, we get 2NH4 plus, we get an SO4 2 minus, we have a zinc 2 plus 2Cl minus, giving us 2NH4 plus 2Cl minus plus zinc 2 plus SO4 2 minus. And I mean, if you now just quickly look, everything can be cancelled. I mean, everything is on every side. So that's there, that's there, that's there, and that's there, and that's there, and that's there. So in principle, there's nothing really actually happening. There's no exchange reaction really happening. It's just on both sides we have all the ions in solution. There's no precipitate actually forming, so therefore there's no precipitate. And that means our net equation, therefore the net ionic equation, is nothing. Therefore, net ionic equation does not exist. Because there's no precipitate forming, we only have a molecular equation. So the molecular equation is this thing out at top here. So there's only a molecular equation, and in principle, all that it actually says is all the ions, like they're written here on the left-hand side, is what are in solution. They're just floating around. There's nothing actually happening there. No reaction taking place. All right. So let's look at C. C is barium sulfide and copper sulfate. Right. So barium sulfide implies that it is barium sulfide. It's an aqueous solution, so it's dissolved. Copper sulfate, SO4, aqueous, giving, so we swap the ions, barium SO4 plus copper sulfide. And now we need to check which one or what is the states or the phases of these. And you'll see that barium sulfate is a solid. Most sulfates with group 2 metals, or specifically barium. And then the sulfide one is also a solid. Copper sulfide is also a solid. All right, so that's our molecular equation. We see we form 2 solids. So let's write the full ionic equation, or the total ionic equation. So on the left-hand side, barium sulfide is able to dissolve, so we can split that into barium 2 plus and S2 minus. The copper sulfate does also do the same, so it's SO4 2 minus and copper 2 plus. And that gives us, we can't split these because they're insoluble, they form precipitates. So SO4 plus copper S. And then, of course, I mean, if they're ions, you put the aqueous, and then if they're solids, they put the solids. And now we eliminate to get the net ionic equation. So barium 2 plus, there's nothing on the right-hand side. S2 minus, there's nothing on the right-hand side. Copper 2 plus, there's nothing on the right-hand side. SO4 2 minus, there's nothing on the right-hand side. And that is because we form two precipitates. If we form two precipitates, there are no spectator ions. So therefore, there are no spectator ions. And hence, our net ionic equation equals the full or the total ionic equation. So your answer is this one at top here, so that means you need to add the phases. There's aqueous, 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 solid, solid. So interesting. So the three situations that we looked at, the first one, there is one precipitate forming and one molecular compound that is still soluble. So we have a situation where we have two ions that forms a solid. The second situation, B, we had that all of them are still soluble. So there's no net ionic equation. It's just, I mean, in fact, there's actually nothing happening. We can think of it as an exchange reaction, but it doesn't really have an effect. And in the final one, we actually form two precipitates. And hence we see that everything then participates in the net ionic equation, and because there are no spectator ions. So that's essentially the three options that you can have. There aren't any other options that can appear or arise. So the basic point here is just to remember how to do the exchange reactions. So you need to swap the ions. Once you swap the ions, check their solubility, and you should be fine. All right. Thank you for watching.